Alright, we're going to continue our examples talking about known cross-sections. We're going to look at example 6, cross-sections that are perpendicular to the y-axis rather than to the x-axis. The region bounded by y equals x and y equals x squared is the base of a solid where cross-sections perpendicular to the y-axis are equilateral triangles. Find the volume of the solid. Okay. So let's draw the region. We've seen this region before. Let's draw it. We know y equals x goes like this through the origin here. Y equals x squared touches the origin and then comes up like this. There is our region. Okay, so this of course is y equals x and y equals x squared. Now it says cross sections perpendicular to the y-axis are equilateral triangles. So they would go like that then. They would go like that, up and down that line. So we know the area of the equilateral triangle we learned is the square root of 3 over 4 times the base squared. And the base is going to be the distance between the two functions. But since we're doing it perpendicular to the y-axis, we need to solve these equations for x. This one's good. It's already solved for x. It's just x equals y. Now here this would be x equals the square root of y. So then b would be the right function, which is the square root of y minus y. That's b. And of course we've learned that volume is accumulated area. We accumulate those areas. So it'd be the integral. And we know that those functions intersect at 0 and 1. From 0 to 1, put the square root of 3 over 4 on the outside, and then b squared, which is the square root of y minus y quantity squared. And you can put that in your calculator, or you can FOIL that out and do the antiderivative by hand on your own. But this is the expression right here. That is the expression. Right? Let's look at another example. Cross sections perpendicular to the y-axis. The region R in the first quadrant, bounded by the functions f of x equals square root of x and g of x equals negative 1/2 x plus 5, is the base of a solid. Cross sections perpendicular to the y-axis are squares. So if I go here this way, it's going to be a square coming out. What is the volume of the solid? Well, you know the area of a square is side squared. So it's going to be the integral of that. But we have to do it perpendicular to the y-axis. So we have to have these functions solved for. This one's y equals the square root of x. So then x equals y squared. We have to have them solved for x. This one is negative 1/2 x plus 5 equals y. So again, to solve that for x, I would subtract 5 and multiply by negative 2. So I'm going to do that up here. So I'd have negative 1/2 x equals y minus 5, multiply everything by negative 2, and I get x equals negative 2y plus 10. Right? So then this is negative 2y plus 10 equals x. That's the function. So that's clearly the top function, and the bottom function is x equals y squared. So what we do is we're going to do the top minus the bottom is going to be s. So it's going to be negative 2y plus 10 minus y squared. And then our integral would just be the integral from 0, and we have to find our other bound, which is going to be the y value of that intersection point. We'll find that in a minute. It is negative 2y plus 10 minus y squared, all quantity squared dy. And we have to, of course, find that intersection point. So we're going to have to graph these functions, graph them in their original form here. Y equals square root of x and negative 0.5 or negative 1/2 x plus 5. We want to graph those on the standard window, so let's do zoom 6 to make sure we're there. And there they are. So we're going to do second trace, number 5, intersect, first curve, second curve. They only intersect once, so, and we want the y value now, 2.31662. So we're going to do 5 decimal places when it's not our answer. When it's an intermediate value, we do 5 decimal places. For our answer, we can do 3 decimal places, truncated or rounded. And again, you can put that into your calculator for yourself, but that is the expression that we need.